Continuing with Coulombs Law, we said that all matter is made up of atoms. We said that atoms have protons, neutrons, and electrons. We're going to be ignoring neutrons for the most part. We said that there are two types of charges, positive and negative. I think I told you I abbreviate the word positive as plus VE. I abbreviate the word negative as minus VE. I don't just use a plus sign and a minus sign if I'm using it as a word, as an English word. Charge is measured in coulombs, and we use the symbol capital Q or lowercase q as our variable for charge. Capital C is the symbol for coulombs as a unit, but as a variable in our equations when you say Q, charge. Why not C? Taken by other stuff. Why Q? Because charge is quantized. We said there is an elementary charge. This is on your formula sheet. You don't need to memorize it, although you probably will for this unit. And it's positive or negative 1.6 times 10 to negative 19 coulombs. Charge on an electron is negative 1.6 times 10 to negative 19. Charge on a proton is positive 6 times 10 to negative 19, which is not big. 0.00000, 18 zeros, and then a 1 and a 6. I did say that there's something called quarks, but we're going to pretend that have smaller charges than that. But Alec, we're going to pretend they don't exist. Then the key idea, we said that charges exert a force on other charges, and we can predict the direction by using, everybody, are you ready? Like charges. Everybody, are you ready? Like charges, unlike charges, like charges, unlike charges. I'm going to keep doing this until I get more volume from the back row. Like charges, more volume. Like charges, okay. Like charges, unlike charges, attract. That you have to memorize. You could write it on your blue sheet, but that you have to memorize. What we're going to do then to figure out the direction of the force, and this is page where my gravity analogy breaks down, because objects can repel, unlike gravity, where they always get attracted in electrostatics, stuff can fall up. It can repel. But that's okay. We'll be able to handle that okay. The question then is, how can we figure out the magnitude of the force? And this is where we left off with Coulombs Law. We said Coulombs Law, which looks a lot like the gravity equation, and that one you want to write down, Jaden, is Fe for electrostatic force instead of Fg for gravitational force. Fe is K, which is just like big G, but a much nicer number. Q1, Q2 over R squared. Does anyone remember what K was? You'll probably memorize that one during this unit. What was lowercase k? 9 times 10 to the 9th. Much easier to type on your calculator. So even though the mathematical concepts will be very, 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 very similar to what we did with gravity, you're going to find the whole bleeding blisters on your thumbs of typing is nowhere near as bad. The numbers are just nicer. By the way, it's actually 8.998 something. You know what? 9. Close enough to 4 sig figs. It's 9. Okay? So we also said that we don't put negatives and positives into the equation, which is why I think on your formula sheet there's absolute value signs. We use the negatives and positives to figure out whether it's attracting or repelling. If they're opposite, attract. If they're like charges, repel. Yes, Linnea? And I think we got to right here. Example 8. Says this, find the force on the electron in a helium plus ion with the radius of that. Okay, that problem is occurring. Let me pause the video. I'm trying the wireless projector adapter. Ira, what does this question, example 8, want us to find? I know I caught you zoning out, that's why I picked on you. Ira, what does this question 8, example 8, want us to find? Force. Which force? Electric force. So we're going to use Coulombs Law. It's going to be K Q1 Q2 over R squared. And now we're at the plug and chug stage as far as I'm concerned, Ira. Sarah, what was K? 9 times 10 to the 9th. Charge 1, Ira, look at the nucleus here. This is where the first set of charges are. How many neutrons are there? 2, but what's the charge on a neutron? So I don't care about the charge on a neutron. Oh, I got a latecomer. How many protons are there in the nucleus, Ira? What's the charge on a proton? Nope. It's on your sheet. This is the elementary charge. So it's going to be 2 protons. What's the elementary charge? It's on your sheet. Find it. No, it's an element. It's on your sheet. Find it. It's the elementary charge. It's on your sheet. Yes. Now, from now on, instead of walking you through those steps, you're going to hear me say with disdain in my voice, it's a proton. And I expect you to clue in, it's 1.6 times 10 to negative 19. Now, we're finding the force between the nucleus, Ira, and this electron. So the second charge, Q2, is an electron. What's the charge on an electron? It's an electron. More specific, please. Same thing. Read it to me. It's an electron. No. It's an electron. Charge, not mass. You're reading me a mass. Do we put the negatives in this equation? Because there's absolute value signs. So try again. It's an electron. Yes. All over. What's R? The question tells us in the question. Don't forget the squared. Get your calculators out. Here we go. Okay? So jogging your memories, I will not tell you the charge on a proton or an electron. That's on your sheet. It's not 1, by the way. It's 1.6 times 10 to negative 19. 1 Coulomb, remember what I said? 1 Coulomb is massive. That if you absorbed 1 Coulomb all at once, you're dead. And you're dead probably pretty spectacularly with like melty skin and sparks and yuckiness. 9 times 10 to the 9th times 2. Ira, in this question here, as a shortcut, I notice I have 1.6 times 10 to negative 19 times 1.6 times 10 to negative 19. By a fluke, because the charges happen to be the same magnitude, I'm going to go 1.6 times 10 to the negative 19 squared. That's not actually part of the equation, but I'll take that shortcut since it's sitting there. Divided by 2 times 10 to the negative 11 squared. Do you get 1.15 times 10 to the negative 6? You get that okay, Ira? Units, it's a force. You get something different, Patrick? Did you put a squared on the bottom? It's R squared. Right, Chang? Did you put a squared right there because I have 1.6 times 10 to the negative 19 times itself? That's not in the equation, but just by this one as a fluke I can do that?
I didn't. I just wrote it out.
Okay. Ira, units for force? Is that a big force? It's massive. Sorry, it's massive to an electron. It's huge to an electron. Ira, F equals what? If I take that force and divide it by the mass of an electron, which is on your formula sheet, Ira, can you find the mass of an electron on your formula sheet if I divide this by the mass of an electron? Negative 31? That's the acceleration. Is that a big acceleration? 1.26 times 10 to the 24th. That's a massive acceleration. To an electron, this is a ginormous force. This is a gargantuan force. To us in our big non-quantum world, meh. But to an electron, that is existence changing. You're changing your path and your movement. So on the next page here, I wrote, although the force you calculated may seem very small, we should note that we're dealing with electrons which have a really tiny mass. If you find the acceleration, it's 1.26 times 10 to the 24th, which I think you'll agree, that's massive. So on atomic terms, Linnea, in atomic terms, this is a very, very large force. I like example 9, I like example 9, I like example 9. Example 9 is a nice question. Gurjo, what does example 9 want me to find? Guys, can you stop talking, please? Thank you. What does example 9 want me to find? Keep reading. Keep reading. Positive 1. What's that thing? In friction, it's mu, but what is it as a metric prefix? This is micro. So micro Coulomb. And the reason I had you read all that is there's 3 charges. It wants us to find the net force on one of them. How many charges are there? You know what you should do? The same thing as we always did when we had more than one mass. Let's label them with numbers. I'm going to call this Q1, Q2, and Q3. The same way as with the Atwood machine, you always heard me say, is there more than one mass? I'm going to call the first one M1. That little bit is always worth doing. So now, which charge does it want me to find the net force on? Q1, Q2, or Q3? Q2. Okay, that we have to be able to do that on your own. That I can't help you with. Say it again. Which charge are we being asked to find the net force on? So Q1 is exerting a force on Q2. Q3 is exerting a force on Q2. They're both vectors. We're going to do them one at a time and then add them vectorially. We call this the principle of superposition. That's a fancy phrase. How many charges are there grand total? We call that the 3-body problem. We have no way to calculate the force from 3 bodies at once. There's a Nobel Prize in physics if you figured that one out. Okay? We have no way to calculate, by the way, the force between 3 planets at once, all at once. We only can do them 2 at a time. We only can find these 2 at a time. So here's what I'm going to do. I'm going to find the force from charge 1 on charge 2. I'll write it 1, 2. Then, on a separate line, I'm going to find the force of charge 3 on charge 2. And then I'll add them vectorially because I'm going to get magnitude and direction for both of these. Are these in a nice straight line? So I won't have to go tip to tail. I'll be able to use the Physics 11 shortcut of winner minus loser. Okay? So electric force is K Q1 Q2 over R squared. Gurjot, what's K? 9 times 10 to the 9th. Charge 1 is 1. And then a microcoulomb is 10 to the negative 6. That part is worth memorizing. It is on your formula sheet where all those metric prefixes are, but trust me, you're going to get about 80% of your charges in this unit in microcoulombs, so that's worth committing to memory. Charge 2 is 1 microcoulomb. Now, Gurjot, I know charge 1 is technically negative 1. Do I put the negative in the equation? No. Divided by, what's R here? What's the distance between charge 1 and charge 2? And please don't say 20 because it's not. Why can't it be 20, folks? Centimeters, so fix it. 0.2? What goes on the 0.2, Chang? Okay. What do you get? 9 times 10 to the 9th, 1 times 10 to the negative 6, 1 times 10 to the negative 6, divided by 0.2 squared. What'd you get, Jaden? Come on, people, got to try this. Did you get 0.225? Okay. Units, Gurjot, it's a force. And now, direction. So, look at charge 2. Temporarily ignore this one. Pretend it's not even there. Which way will charge 2 feel a force because of that one? Are they like or unlike charges? Unlike? Unlike charges, what? So will this feel a force to the left or to the right? Now we're going to repeat that for the force on charge 3 on charge 2. I'm not going to rewrite the equation. Let's see if I can just go with the numbers. K is 9 times 10 to the 9th. How big is charge 3? 2 microcoulombs. Charge 1 is still 1 microcoulomb. Gurjo, what's R between charge 2 and charge 3? Don't say 10. Chang, what goes on the point 1? Okay. Hey, you know what? We can use our backspace and edit trick here, because I think the only differences are I changed that one to a 2, and I changed the 2 on the bottom to a 1. That works. And I get, much bigger, 1.8 newtons. Oh yeah, it's closer, and the charge is larger. It should be bigger. Direction. Look at charge 2, look at charge 3. Are they like or unlike? Unlike? So is charge 2 going to be pulled to the right or repelled to the left? How will I add 1.8 newtons to the right plus 0.225 newtons to the left? I think I'll just go winner minus loser. What if they were in the same direction? Winner plus winner. What if they aren't in a nice straight line? Well, I would take those two vectors and do what? Add them. So I can handle whatever you throw at me, and there will be probably one where I make you do a tip to tail, but only one. I'm not going to do a gazillion of those. If we can handle one, we can handle a gazillion. So for now then, F net is going to be 1.8 minus 0.225. I can do that in my head. I think it's going to be 1.575. I'll call it 1.58 newtons, and the winning direction is to the right. This concept, Sarah, of me giving you 3 charges, but you can only do 2 at a time, that's hugely important. We're going to be doing that an awful lot in this unit. The fancy word for that is the principle of superposition. I think I include that in another lesson just for nerd trivia, but 2 at a time. You'll notice, by the way, I don't care. I know that this charge and this charge are exerting a force on each other. I don't care about that. That's not what the question asked. The question said, find the net force on the second charge. So I don't care what 1 and 3 are doing to each other. Not even part of my equation. Is that all right? Turn the page, or next page over. Here's a nice thought puzzle. At which point, approximately, could we place a positive 1 microcoulomb charge so that it would experience no net electrical force? Hey, this is a little bit like the bonus question on your test. Where between the Earth and the Moon would there be no net gravity? Let's see if we can figure this out. You know what? I'm going to figure this out purely with a process of elimination. In my mind, or you can do this actually, I'm going to put a positive charge right there at location A. Alec, my friend. Oh, you know what? Let's also call this Q1, Q2. Alec, my friend, Q1, positive or negative?
Negative.
What charge have I put right here?
Positive.
Which way will this charge feel a force from Q1? Attract to the right or repel to the left?
Attract to the right.
Why? Because they are?
Unlike.
Yes! So all of you right now, draw a little vector arrow pointing that way. That's the charge, that's the force from Q1. I don't know how big it is, but I can tell you that's the direction. Alec, my friend, my test charge and Q2, like or unlike? So which way will this feel a force from Q2? Attract to the right or repel to the left?
Attract to the right.
Now, is there any way that I can add right plus right and get 0? Is there any way that I can add right plus right and get 0? Is there any way that those two forces can cancel each other out? Can't. You know what? Let's be nice and symmetrical. Let's go to location E, because I have a feeling it might be a similar argument. So I'm going to go right here and put a positive there. Patrick, my friend, like or unlike charges, those two?
Unlike.
So which way will this positive feel a force?
Left.
To the left? What about if I look at that guy?
Unlike.
So also to the left. Is there any way that I can add left plus? Where do you think there's going to be no net force? Which two locations are likely? B or D. Now let's tackle those. What do you want to try first, B or D? Pick. B. So let's put a positive there. These two charges, like or unlike? Alike? Or sorry, unlike?
Yeah.
So which way will this feel a force?
To the left.
Good. These two charges, like or unlike?
Unlike.
So it'll feel a force to the?
Right.
Now pause. You ready? Is this distance bigger or smaller?
Bigger.
So the force will be weaker. Wait. But this charge is.
Stronger.
So you know what? Yeah, I'm leaning towards that one, I think. But let's do a double check. Let's quickly test location D. Here I would be big attraction because the charge is twice as big and we're closer. Here I would have small attraction. Although those are in opposite directions, I don't think they're going to cancel out. I'm going to say location B. And my argument is what I just walked through. By the way, location C, which way would be the net force? Let's see. If I put a plus there, it would get attracted that way and attracted that way. Are those two forces at angles to each other? How would I add them together then? Tip to tail, you say. So I would have something like that plus that. I think the resultant would be kind of something like that. I need more numbers to be more specific, but I can handle it. But I agree with you. B. Yes? Well done. This is why I hate warm rooms. So many of you are yawning. As I look around, I see a whole bunch of people. Wake up, take your jacket off, and stay a while. Example 11. Sarah, can you tell at a glance that this is probably going to be adding vectors tip to tail? Why can you tell at a glance that that's the case? Because these three charges are not in a nice straight. Not. Okay. It wants us to find the electrical force, magnitude, and direction on the electron shown below. Gurjot, how many charges do I have in this picture? How many charges do I have in this picture? 3. What should I do first before I even start? Let's label them. You know what? Since the electron is the one I'm interested in, I'll call that Q1. I'll go down Q2. I'll go right Q3. Doesn't matter what you label them, but let's all label them the same in our picture so that we're using the same thing. Sarah, what does this want me to find the force on? Charge 1. We're going to use the principle of superposition, which means I'm going to go 2 at a time. I'm going to temporarily ignore that guy. I'll find the force that charge 2 puts on charge 1. Then I'm going to temporarily ignore that guy. I'll find the force that charge 3 puts on charge 1. I know these two are exerting a force on each other. I don't care. Not what the question asked. Follow it? Okay, so how can I write organized but not write much? I'll say this. I'm going to find the force from charge 2 on charge 1. Do you already have the equation somewhere on this page? Have we written somewhere on this page K, Q1, Q2 over? Okay, Sarah, what's K? Charge 1, 1 microcoulomb. That's going to be 1 times 10 to the negative 6. Oh, sorry, that's not charge 1. Ira, it's an electron. Please show her where it is. Leia, can you show her where it is on your sheet, please? Yes. Yes! What was that, Ira? Sarah, charge 2, 1 microcoulomb, 1 times 10 to the negative 6. Now, this is interesting. How far apart are they? It's not 2 meters. It's 2, what's that little funky symbol? Micro, which means I just replaced that with a 10 to the negative 6 as well. It's 2 times 10 to the negative 6 Chang?
Squared.
You know what I'm going to do is I'm going to give myself more room so I can do this on one line. Let's see. You know what? I can backspace and just edit some of this, can't I? It's going to be 1.6 times 10 to the negative 19, 1, 10 to the negative 6, divided by 2, 10 to the negative 6 squared. Do y'all get 3.6 times 10 to the negative 4? Yes? Units, Sarah? It's a force. Did you say newtons? Now, last thing. Direction. So look at the electron. Which way will it feel a force because of that guy? Down attract or up repel? Okay. You know what? So are we going to be adding these tip to tail? Is that what you said? Let's be clever. Let's put in a little compass rose here, because that way instead of up and down we can use, because I think we're going to do our degrees what of what, north of south, east of west, what of what. So revise your answer from down to south. We repeat. We're going to find the force of charge 3 on charge 1. It's going to be 9 times 10 to the 9th. Ira, what's the charge on charge 1? It's an electron. What if it was a proton? Yep. Which one of those is negative technically? Do I put the negative in the absolute value? No. You'll notice, though, not every formula has absolute values, which means some of them later on we will include the positives or negatives. If it's a scalar and energy, we need to. 1.6 times 10 to the negative 19. 2 microcoulombs all over. Same distance. Chang?
Squared.
So this, again, that backspace trick works well. In fact, I think it's going to be 7.2 because it's just going to be twice as big. Yeah? 7.2 times 10 to the negative 4 newtons. Sarah, direction. Attract toward east or repel away west. Are they like or unlike? Because which of these is actually a negative? Yeah, an electron is negative and this is negative. I think it's going to be to the west. Yes? And now let's finish this off, Sarah. I need to add these two together. How would I add them together? Draw them. Draw them tip to tail. Tip to tail. I'm going to go south and west. I got room here. I can do a good triangle. Do a fairly big triangle if you can. So, which one of these is bigger? The west line. So I think it's going to look something like this. 3.6 times 10 to the negative 4. Yeah, about twice as long. That should be dead horizontal. I suck at drawing these, Stephen, obviously. 7.2 times 10 to the negative 4. And the resultant is always from the tail of the first. There is my net force. Where am I going to put theta? Bottom left or top right? Where does theta go? This is great review. Yeah, always where the vector is originating from. By the way, that theta, north of south, east of west, what of what? It's either south of west or west of south. Oh, the of blank is the nice line, so south is the nice line. It's going to be something of south, west of south. Okay, you know what? I'm so clever. I'm going to go like this. F equals, and then I'm going to say at west of south. I think, are you folks okay doing the Pythagoras showing no work? That number squared plus 3.6 times 10 to the negative 4 squared, square root. Oh, sorry. I did that totally wrong. 7.2 Chang?
Squared.
Plus 3.6 negative 4. Chang?
Squared.
Equals that number squared, square root. How could I have missed that? That was terrible of me. I get 8.05 times 10 to the negative 4. The emotional scarring I do to you folks is amazing, isn't it? 8.05 times 10 to the negative 4 newtons. I think I can go tan. It's going to be opposite adjacent. Is this kind of nice familiar territory, Jaden? We did a whole bunch of these before Christmas. This is also, I mean, 'cause we're getting towards the end of the year. It's kind of nice to review some of our vector skills. So it's going to be tan theta equals opposite 7.2 times 10 to the negative 4 over adjacent 3.6. Hang on. Mr. Dewick, can I cancel out the 10 to the negative 4s before I do the trig? You know what? Let's find out. You folks, this half of the room, can you do shift tan of 7.2 over 3.6? This half of the room, can you do shift tan of 7.2 times 10 to the negative 4 over 3.6 times 10 to the negative 4? Do we get the same answer? What'd you get for theta, Weil? What'd you get for theta? 63 point something. Okay, and all of you did too much work, Ange. You don't know what I did? Wow! Yes, you can simplify fractions before you do the trig, and you often will find your 10 to the powers of will match each other on top and bottom. But there often will be 10 to the powers of, because 1 Coulomb is so massive, I'm almost never going to give you a 1 Coulomb charge. I'm going to try and be realistic. Most charges, the ones you get with static cling and things like that, they're in the micro Coulomb range. So 63.4. I'm going to put, I think, 1 like that on your test, but not 10. It may be a tip to tail for electric force, or you'll learn tomorrow about electric field. It may be that. What's your homework? What did I assign my block Ds, Mr. Dewick? I went 1, 2, 3, 5, 6, 7, 8, 10, okay. 1, 2, 3, skip 4. 5, 6, 7, 8, skip 9, or as I like to say, 9. Nothing. Okay. 10, 11, 12, 13, 14. So what did I skip? 9 and 4, right? So let's do that for you folks. Circle number 1, 2, 3, skip 4. You actually got a fair bit of time to work on this. And I brought out the Van de Graaff with you last day, right? I think it was Paige that got a pretty good shock because she was wearing a ring. Yeah? Okay. So I won't bring that out again. Although I got to say, yesterday afternoon... Oh, no, we had a dry day with you folks, too, didn't we? Yesterday afternoon, I brought it out with some guests, and wow, I had to be careful. I was getting shocks just standing nearby trying to turn the machine off. I took a few.